In our last videos, we took a standard ESP32 and used deep sleep to slash its power usage by 99%. But look closer. That dev board is still wasting precious energy. What if we could rip out everything we don't need? What if we could build our own board from the ground up for one single purpose, ultimate battery life? Today, we're on a quest to hit 5 microamp deep sleep. This is the complete journey, from a blank screening KiCad to a professionally assembled PCB in our hands from the pros at PCBWay. And I'm giving you everything, the full KiCad source files, absolutely for free. But first, I just want to take a moment to say thank you for being here. Every view, every comment, every like genuinely helps this channel grow. I'm just one person in my workshop sharing what I learn. When you click that like and subscribe button, it does more than just help the channel grow. It tells me that these videos are actually helping you. I promise you I read every single comment, and your feedback directly shapes what we explore next. So thank you for being a part of this. It truly means the world. Alright, enough talk. Let's build the ultimate low power ESP32. So why can't we hit our 5 microamp goal with a regular dev board? Because they're built for prototyping, not for production. They're loaded with power-hungry extras. First, the voltage regulator. It's essential for USB power, but it's always drawing a tiny bit of power just by being there. It has to go. Next, the USB chip. Super handy for programming, but for a project running on a battery in the middle of a field. It's a useless power vampire. Gone. And the most obvious one, the power LED, a constant, pointless drain on our battery. We're getting rid of it. Our strategy is simple, addition by subtraction. But this creates two very important challenges we have to solve before we even think about designing. Challenge number one, power. Without a voltage regulator, we can't just plug in any battery. A standard 4.2 volt LiFePO would instantly fry our chip. We need to supply power directly in the ESP32 safe zone, between 3.0 and 3.6 volts. Our weapon of choice is this, a 3.2 volt LiFePO4 battery. But even these need care. We'll need a battery management system, or BMS, to make sure it never charges past 3.6 volts. Challenge number two, programming. We chopped off the USB port, so how do we upload code? We need one of these, an FTDI programmer. It's an adapter that lets us talk to the board directly. Before I spent a single dollar on a PCB, I had to make sure I could solve these two problems. It was time for some prep work. A quick check with the multimeter confirms the battery voltage is right in the sweet spot. Perfect. Test 2, the programmer. The last thing I wanted was a box of coasters I couldn't program. So I practiced on a regular dev board first. A few wires, a click of the upload button, and boom. It works. It's reliable. With our risks managed, we are clear for takeoff. It's time to bring this board to life in KiCad. Alright, let's dive into KiCad. It's an incredibly powerful and totally free tool for designing PCBs. If you're new, I highly recommend their official Getting Started guide first. First things first, we need the brain of our operation. We'll add the official Espressif libraries to get the exact footprint for our ESP32 C3 Mini 1 module. For everything else, resistors, buttons, capacitors, I use a fantastic resource called SnapEDA. I'm choosing components I know I can get from suppliers that our manufacturer, PCBWay, works with, like Mouser or DigiKey. This will make the assembly process 1,000 times easier. Now we just play connect, the dots, replicating the essential parts of the official dev kit schematic, but only the parts we need, the boot and reset buttons, pull-up resistors, and of course headers for all our GPIO pins. Before we move on, we run the electrical rules check. It's like a spell checker for electronics, and it gives us the green light. With the brains done, it's time to give it a body. We hit Update PCB from Schematic, and KiCad gives us all our puzzle pieces. Now for the fun part. Step 1. We draw the physical shape of our board on the edge cuts layer. Step 2. Component placement. This is a game of Tetris, arranging everything for the cleanest connections. Step 3. Routing. We're drawing the actual copper wires that will bring our circuit to life. We'll use vias to jump between the top and bottom layers to keep things tidy. Step 4. A ground plane. This big area of copper is connected everywhere to ground, which makes our board more stable and reliable. Step 5. The silk screen. We'll add labels for every pin and a logo to make our board look professional and easy to use. One last check with the design rule checker to make sure our layout meets the manufacturer's specs and we are ready to export. Now for a step that trips up a lot of beginners, getting the right files for the manufacturer. You need gerbers, a bill of materials, a pick-and-place file. It's confusing, but watch this. PCBWay has a KiCad plugin that does everything for you with one click. It bundles all the files we need into a perfect little zip file. We head over to the PCBWay website and upload that zip file. Their system instantly analyzes it and gives us a full cost breakdown. You can see the price for the boards, the components, and the assembly labor all right there. We're choosing the full turnkey PCB assembly service. This is the easy button. It means I don't have to hunt down and order every single tiny resistor myself. PCBWay's team handles all the component sourcing. Their process is amazing. An engineer runs a DFM designed for manufacturability check on your files to catch any potential problems. My customer care rep was super helpful and communicative the whole way. They even sent me this photo of all the components laid out on the board for my final approval before they started soldering. The shipping was fast, and the final quality was immaculate. This isn't a hobby project anymore. This is a professionally manufactured product. But does it work as designed? Alright, test number 1. Does it even work? We'll connect our FTDI programmer and upload a simple blink sketch. Yes, we have life. For a bit of fun, I'm actually using the Morse code sketch from our previous video to have it blink my initials. You can find a link to that in the description. Next, test number 2. Is the Wi-Fi working? I'll upload the ThingSpeak data logging code from another tutorial. And there it is. It's connecting to my network and sending data. The MCU and the antenna are working perfectly. You can also find a link to that data logging video in the description. And now, the ultimate test. The reason we did all this, can we hit 5 microamps? I'm uploading the deep sleep code from the very first video in this series. I've got my multimeter connected in series to measure the current. Here we go. Okay, while it's awake, we're drawing about 18 milliamps. Normal. Now, watch what happens when it goes to sleep. Whoa, 0. The current is so low, this scale can't even measure it. Okay, let's switch to the super sensitive microamp setting. Wait, what? It's resetting. Every time I try to measure it, the board browns out and reboots. What is going on? After some research, I found the culprit. The multimeter itself. On these sensitive settings, its own internal resistance was causing just enough of a voltage drop to crash the ESP32. To solve this, we need to go full mad scientist with our power delivery. I built a regulated test bench using a 9-volt power supply and a buck converter, dialed in to exactly 3.55 volts. But even that wasn't enough. I also had to add a chunky 220 microfarad capacitor to act as a buffer for the current spikes. Now, capturing the reading requires a bit of tactical maneuvering. If I start on the sensitive 2 milliamp setting, the board won't boot. So, I have to prime the circuit on the 20 milliamp setting first. Okay, it's awake, drawing 18 milliamps, and sleep! Quickly switching to the 2 milliamp range. Steady, steady. There it is, 5 microamps. We got it. And crash. As soon as it tried to wake back up, the range switch caused it to brown out. But it doesn't matter. We held stable deep sleep and we captured the data. We have officially proven the concept. To put that into perspective, the original development board we started with was great, but it bottomed out at 30 microamps. By designing our own PCB, we just slashed that deep sleep current by another 83%. This is the difference between a smart sensor that you have to climb a ladder to change the batteries on every few months, and one that you can deploy in a remote field and forget about for years. I know we've covered a huge amount of information really quickly, from KiCad design to advanced testing. If you want to go over all of this at your own pace, with detailed explanations and all the links and files ready to copy and paste, you're in luck. I've written a massive companion article on my website that goes through every single step in detail. You can scan the QR code on your screen right now, or just click the link at the top of the video description to check it out. So, the big question, Was it worth it? We went from theory to a physical ultra-low power board in our hands. We learned how to design a schematic and a PCB, how to use a custom PCB prototype assembly service, and how to solve real-world testing problems. For any serious battery-powered IoT project, designing a custom PCB isn't just worth it, it's an absolute game changer. You gain ultimate control over power, size, and function. Now, it's your turn. What will you build with a truly long-lasting ESP32? A remote weather station that runs for years? A smart mailbox notifier? Let me know in the comments below. I've put all the project files for you on GitHub. And if you want to build this exact board, it's a shared project on PCBWay. Don't forget, there are links for all of that, plus a referral link for a $5 credit on PCBWay in the description. Thanks for joining me on this journey.